Okay, today our focus is going to be on factoring and using graphing technology to help us solve the polynomial functions that we've been looking at. So we did pull real solutions off of the graph, emphasizing finding the x-intercepts, but algebraically sometimes we need to be able to find exact values that we don't see on the graph or when we don't have a graph. So here's a polynomial equation, and we're going to solve it using factoring. So the first thing I'm going to do is add 21x squared to both sides so that I have everything on one side and z equal to 0, so I can use that zero product property. So 3x squared is the greatest common factor of the polynomial here, and that leaves x squared minus 4x plus 7. I could try to factor x squared minus 4x plus 7, but there are not two numbers that multiply to make 7 and add to make negative 4. So it's not factorable. That doesn't mean it's not solvable. It means it cannot be factored. So basically, I can set 3x squared equal to 0 to find some solutions. And I need to think about this x squared minus 4x plus 7 when it is set equal to 0. So 3x squared set equal to 0, if I divide both sides by 3, and take the square root, since it's 0, I'm just going to get 0. Okay? But because this came from a squared factor, I do need to recognize this has multiplicity of 2. Because if I was going to sketch the graph or I wanted to know how it behaves at that point, it would be differently than if it was just a normal 0 where it passes through. So since x squared minus 4x plus 7 is not factorable, I'm going to go ahead and use the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. So I have a 4 in the denominator, I have 2. And underneath the radical, I have 16 minus 28, which is negative 12. So if I was only looking for real solutions here, I would stop. This doesn't really say. So I'm going to continue finding all of the solutions. So 12 breaks down to 4 times 3. Because of the perfect square of 4, a 2 can come outside the radical. So I'm going to have 4 plus or minus. Now, a 2 comes outside the radical as well as an I, because the radical had a negative 1 inside of it and 3 doesn't come out. And so this simplifies to be 2 plus or minus I rad 3. So I have 3 solutions to this quartic polynomial, 0 and 2 plus or minus I rad 3. 0 has a multiplicity of 2. They didn't ask, but I say that to recognize that if you listed 0 twice, you would have 4 solutions here, which is the maximum amount a quartic can have. And if you did have to sketch this graph or something, it would give you some insight into the behavior. All right, so while we're going about factoring and we come across these higher order polynomials, there are 2 new factoring patterns that you need to learn. I'm going to go ahead and give you the factoring pattern, and then you guys can multiply it out to see how it works. So the sum of cubes means you have a perfect cube being added with another perfect cube. Okay? Our factoring pattern says this is going to factor as the cube root of each of those, okay, with the same sign between them. And then here, if you square the first term, square the last term for the last, and multiply them together in the middle. You use the opposite sign, and then the last term is always positive. So why does this work? Think about multiplying this back out. You need an x cubed at the beginning. So the x times the x squared will give us x cubed. Okay? Then you need everything to cancel. So as you distribute this x through, you need it to make everything of an opposite sign that y will make when it goes through. So we've already done x times x squared. Okay? When we do x times xy, we're going to get x squared y. Okay? When the y multiplies the x, we'll also get an x squared y. We need one of those to be positive and one of them to be negative. That's why this negative sign showed up here in our formula. So that helps take care of that. Then when x multiplies y squared, we get xy squared. We need a negative one of those to even it out, and that will happen right here. And then finally, when the positive y multiplies the positive y squared, we'll get positive y cubed. So we will have everything cancel out except for our x cubed plus our y cubed. So similarly, we have the difference of cubes here, x and y. We have the same setup. Notice the pattern doesn't look different so far. The only difference here is going to be the signs. And again, that's because we need this last y times this y squared to give us a negative y cubed. And then here we want to pop x cubed, so we have that. And again, we want all the middle terms to cancel out, so that's why we need a positive here, so that as this negative is distributed, the positive gives us all those terms that will cancel out. So you need to memorize these factoring patterns. So make flashcards if you need to, or sit with them for a while. But we have to be able to use this when we recognize that polynomials have perfect cube patterns in them. And here's why. Let's say we go to solve this equation. Some of you might divide both sides by 2 and then take the cube root. Okay? That works if you're looking for real solutions. So if you're just looking for places where it crosses the x-axis, that should be fine. However, if you're looking for all of the solutions, real or complex, there are more solutions than you'll see. So notice that if I solved this just by dividing by 2, and then taking the cube root, I would get one solution, that x is equal to negative 3. That is the one real solution that exists, but this is a cubic polynomial, which means it can have up to 3 solutions. Those other solutions are complex, and the only way that I would be able to find them is through factoring. So watch instead of solving it the way I did, I'm going to bring the 54 to the same side as the other terms because I'm going to go towards factoring. When I factor, see, 2 is a common factor. And notice that x cubed and 27 are both perfect cubes, okay? X cubed is from x being cubed, and 27 is from 3 being cubed. So 3 and x are the values that I'm going to use in that factoring pattern that you saw before. So the 2 is still here. And if you look back at our notes, our factoring pattern says because it's x cubed plus 27, we're going to do x plus 3. And that's going to be times x squared, 3x, and then 9. Because this was a positive, this one's a negative, and the last one's always positive. That's how it will factor. So now 2 cannot be set equal to 0. It's equal to 2. But x plus 3 can be set equal to 0 and find that negative 3 is a solution. That's the same solution I found previously. But when I set x squared minus 3x plus 9 equal to 0, it's not factorable. And if I go to solve using the quadratic formula, I will see what my other possible solutions are. So I get 3 plus or minus a radical over 2. And in my radical, I have 9 minus 36, which is the square root of 27, negative 27. And if I simplify that, because remember 27 breaks down to 9 times 3. It's negative in here, sorry. So I'm going to have 3 plus or minus 3i rad 3, and in the denominator 2. So I have these 2 complex solutions with this one real solution. I would not have been able to find all of the solutions, including the complex ones, without factoring using this pattern. All right. We're going to find each real zero and relative maximums and minimums for these equations using the calculator. So let's go ahead and take a look at that. We're going to first have to plug them into our calculator. So I'm going to go ahead and go to my calculator, go to my y equals, and clear out whatever is in there. And I'm going to put in our first equation. So it was 2x cubed plus, actually we're not going to do part A, sorry, I think there's a typo there. So let's just look at part B. So we're going to do 3x to the 5th minus 5x to the 4th Oops, and I'm typing in my exponent. So let's try this again. 3x to the 5th minus 5x to the 4th minus 2x to the 3rd plus x squared minus 6x plus 8. All right, I'm going to press graph and see what I can see here. All right. Not too bad. Notice I really don't need to see as much to the left and the right, so I'm going to make my x minimum closer to 0 and my x maximum closer to 0. And I would like to see up higher on the y-axis to see where it turns around. So in my window, I'm going to change my x minimum to -5 and my x maximum to 5. And on my y scale, the negative part was fine, but I want to see up higher. I'm going to go up to like 20. And let's see what I can see now. All right. So there's more clarity to what's going on. So we have 3 real zeros that I can see where the equation is crossing the x-axis. I have a relative maximum up here and a relative minimum down here. So we're going to go ahead and find each of those things. So first, let's go ahead and find our zeros. So remember, we go second calculate, and we tell the calculator we want to find a 0. So I'm just going to go from left to right. So I'm going to scroll over to the 0 that's furthest to the left. It wants a left bound, so I'll scroll to the left and press enter. Then right bound, and then guess. And so remember, when it says something like this, y equals 2.2 e negative 12, that means 2.2 times 10 to the negative 12th, which is a decimal with 11 zeros and then a 2. So that is basically 0. So it's giving us this point. So our 0 is at negative 1.24, comma 0. We'll go ahead and find the other ones using the same manner. So you're going to keep going, second calculate 0. The difference is you're going to scroll over to other zeros on the graph, but you're still going to do the same procedure. You need to mark a left bound for the calculator and a right bound, and then have it guess. So this second 0 here is going to be 0.93, comma 0 as a point. And then the last 0, okay, left bound, right bound, guess, and 2, 0. And then it also said to find the relative max or minimum. So we're going to go second calculate, and we'll go ahead and choose minimum. So I'll do the relative minimum first, and again, I need a left bound and a right bound and to guess. So it appears that the relative minimum is at the point 1.62, comma negative 8.56. And then I'll repeat the same thing for the relative maximum. Sorry. All right, so second calculate, and this time I'm going to choose choice 4, which is maximum. And I'm going to scroll over to the relative maximum. And, oops, I went too far, sorry. I'm going to mark a left bound. Sorry, I went way too far. My computer wasn't scrolling as fast as I was. All right, here we go. All right, so for this relative maximum, there's a left bound. Here's something to the right. I'm going to press that I want it to guess. And it will give me a relative maximum of negative 0.7, 11.67. So I would mark those things down. So again, we didn't do part A, but for part B, now as a recap, our zeros, there were 3 real zeros, where x equals negative 1.24, 0.93, and 2. Our relative minimum point was 1.62, negative 8.56. And our relative maximum point was negative 0.11.67. Okay, so lastly, here's a word problem that kind of uses this idea. What are 3 consecutive even integers whose product is 4 times their sum? So if you have an integer, the next even integer would be that number plus 2, and the next one would be that one, the original one plus 4. So this is the way we can write consecutive even integers. And then it says the product is 4 times their sum. So when you multiply them all together, that's equal to 4 times the amount you get when you add them all together. And then I'm going to go ahead and try and simplify and solve this equation. So when I combine like terms right here, I get 3x plus 6. And over here, I'm going to get x times x squared plus 6x plus 8. Multiply it out on the side if you're not sure. So I'm going to have x cubed plus 6x squared plus 8x equals 12x plus 24. I'm going to subtract 12x and 24 to gather all the terms on the same side of the equation. So I'm going to have x cubed plus 6x squared minus 4x minus 24. So now I'm going to work to factor this. If you don't remember how to factor things that have 4 terms in them, I'm going to go ahead and factor this by grouping. So I'm going to look at this first group and say its greatest common factor is x squared. And when I factor that out, I have left a factor of x plus 6. And in this second group, I'm going to factor out a negative 4 that leaves me with a group of x plus 6. Now when I look at this large term and this large term, they have a common factor of x plus 6. And then they're left with, x squared minus 4. And this x squared minus 4 is the difference of squares and can factor as x minus 2 and x plus 2. So now I have 3 factors, so 3 things being multiplied that equal 0. So either the first factor equals 0, which means x would be negative 6, or the second factor equals 0, which means x would be 2, or the third factor equals 0, which means x would be negative 2. These are not your 3 consecutive integers. These all represent x, which means there's actually 3 possible solutions to this problem. Either the first integer is negative 6, which means the next one's negative 4, and the next one's negative 2, because those would be 3 consecutive even integers. Or the first one is 2, and the next one is 4, and the next one is 6. Or the first one's negative 2, the next one's 0, and the next one's 2. And you can check. For each of these sets of numbers, multiply them together and see if that's equal to the same thing as if you multiply 4 times their sum. And in each of these cases, it is. So there's 3 possible answers to this problem.